Hi, welcome to manufacturing processes. Today we are going to learn about the riser design of the riser and centrifugal casting. Let's take a look at the sand mold casting. First, let us become familiarized with this diagram once again so that you will understand the design of the riser. Okay, the is a flask basically. This is the top one is called cope. This is the cope, and this is the drag, and the assembly of the cope and drag is called a flask. And this is the cavity, this is the sprue, and this is the riser, and this is the mold cavity, and this is the core. So essentially in a sand mold casting, what one does is that you melt molten metal in a furnace and pour the molten metal into this cavity. This is a pouring cup and sprue, and then the runner, and this is the riser, and this is the runner and a gate into the mold cavity. That means molten metal will flow into this mold cavity and then solidify. See what happens when the molten metal solidifies. As I told you, most of the metal they shrink during solidification. Exception to this rule is only the bismuth, silicon, and some more materials. Okay, so the most metals they shrink after the filling is complete into this mold cavity. It's going to shrink. So as it shrinks, you need to supply the molten metal from the riser into this mold cavity. The purpose of the riser is to act as a reservoir of molten metal and supply the molten metal during solidification and during cooling, during solidification, during pouring into the mold cavity. Okay. Now, having said that, if the liquid metal is not fed to the casting cavity during solidification, shrinkage cavities will form. The region where the casting will remain hottest till end of solidification is called hot spot. Shrinkage cavities will form at hot spot. The foundry engineer's job is to design the riser such that the hot spots occur in the riser but not in the casting. We have to design the riser in such a way that the solidification metal should start from the farthest point of the casting when measured from the feeder and move the solid liquid interface front to the top of the riser. The riser must not solidify before the casting. The riser volume must be large enough to provide a sufficient amount of liquid metal to compensate for shrinkage in the cavity. The pressure head from the riser should suppress shrinkage cavity formation and encourage complete cavity filling. Three different approaches exist for design of the riser. The first one is Keynes method, second one is modulus method, third one is naval research laboratory method. So let us focus on the Keynes method. Chevernos has shown that the solidification time of a casting is proportional to the square of the ratio of volume to surface area of the casting. The constant of proportionality called mold constant depends on the pouring temperature, casting, and the mold thermal characteristics. Keynes method continuation. The local solidification Ts is equal to a constant and the square ratio of the volume to the surface area. So where the Ts is solidification time in seconds with the volume of the casting, SA means this SA is correspond to surface area, and the K is the mold constant. The freezing ratio X of a mold is defined as the ratio of cooling characteristics of casting to the cooling characteristics of the riser. X is defined as the riser should solidify last and hence its freezing ratio should be greater than unity. Based on the above, the X is basically the surface area of the casting to the volume of the casting divided by the surface area of the riser to the volume of the riser. The riser should solidify last and hence its freezing ratio should be greater than unity. Based on the above principle of Chevernos' rule, Keynes developed an empirical relationship. The freezing ratio is given the X is equal to A divided by Y minus B minus C, where Y is volume of riser to volume of casting, A, B, and C are constants whose values for different materials are given in table. The equation when plotted will be a curve. For example, the A, B, C constants for different materials like steel, aluminum, cast iron, brass, gray cast iron, aluminum, bronze, and silicon bronze. The values are given. For example, for steel, the A constant is 0.1 and B is 0.03 and C is 1.0. Similarly, for different materials like aluminum, cast iron, brass, gray cast iron, aluminum, silicon, bronze, the values of A, B, and C are given. The line shows the locus of the points that separate the sound castings and castings with shrinkage in steel castings. Take a look at this. Here is a graph for the freezing ratio versus volume of the riser to volume of the casting. And so what happens? These are all shrinkages and these are all sound castings. So what we have to do, if we want to design a sound casting, so based on given a freezing ratio, so suppose that the freezing ratios are about 1.5, that X is 1.5 after you calculate, and go vertical like this, and somewhere here you are going to, anything above this curve, towards this side of the curve, you are going to have a sound casting. So suppose if my freezing ratio after calculation is 1.5, so I would like to somewhere in this area, so this I horizontal read it, so 0.6 let's say. So 0.6 should be the volume of the riser divided by the volume of the casting. We know the volume of the casting, okay? The volume of the riser can be calculated based on this 0.6 value. So essentially we are going to assume that the height of the riser and the height of the diameter of the casting are same, equal. So from this we can always calculate for a sound casting what should be the volume of the riser. So this is the Keynes method. The second method is a modulus method. Here the riser can also be designed by modulus method. Modulus of riser is equal to volume of riser divided by the surface area of the riser. Consider a cylindrical shaped riser with a diameter d and a height equal to its diameter. So modulus of the riser is given by pi d squared by 4 by d divided by pi d squared by 4 plus pi dt. So where the d is the diameter of the riser and also is equal to the height of the riser. Modulus of the riser reduces to d divided by 5, which is equal to the modulus of the riser is equal to 0.2d. We can write like this. Desirable relation to produce a good casting without shrinkage porosity is modulus of riser is equal to 1.2 times mc. So where mc is the modulus of casting and 0.2d is equal to 1.2 mc, or we can write d is equal to 6 times mc. So this is modulus method. So the modulus method, let me go back once again. The modulus method reduces to diameter of the riser is equal to 6 times the mc, modulus of the casting. The third method is the Naval Research Laboratory method. It's a simplified version. Another method was proposed. The maximum length, width, and thickness of the dimensions of the casting section are measured. Say the casting sections will vary, but you will take the maximum length, maximum width, and maximum thickness. Then you will calculate the shape factor. Shape factor is equal to length plus width divided by the thickness. So once you know the shape factor from the graph, shape factor, we have got a graph that the shape factor versus riser volume divided by the casting of the volume, which reads the vertical axis value for a given shape factor. From that, we can calculate the diameter of the riser. Let's look at this thing. Suppose if you know the shape factor, you will know shape factor because you need to measure the maximum length, maximum width, and maximum thickness in a cross section of the casting. So you know the shape factor. Suppose if the shape factor is, let's say, 16. So you go vertical on this graph and there's a minimum and maximum. So the maximum, if you take it, It's going to be like 0.